Hi, I'm Jonathan Oxer, and this is SuperHouse. Automation to me means that your environment or your house or whatever can adjust to circumstances. It can change its behaviour without you having to manually tell it what to do. I mean, that's what automation is, right? It's not just a matter of pressing a button and then a light in another room turns on or off, or even doing it from around the world. That's just being a big remote control. So in order to have a proper automation system, what you need is some form of input, like sensors. So there is one really handy way you can do that. It's a really good way to get started. If you've already put some of the building blocks in place and now you want to add some automatic behaviours into your automation system, what you can do is grab yourself some of these. These are passive infrared motion detectors that are used in alarm systems. They typically go up in the corner of the room. Someone walks into the room when the alarm is set and the alarm goes off, the police are called or the security company. But these things are pretty cheap, they're 20 bucks, give or take. They're really easy to use, and the output is really just a little relay output, which is like a switch. So it's very easy to wire up to any kind of automation system so that you can have your house turn on the lights as you walk into a room. And then what you can do is extend that. Depending on the type of automation system you have, you might do something like have one of these in the passage, and if it detects motion after, say, 11 PM or 12 PM, it will turn the lights on, but only at, say, 20% illumination, because it assumes that you just want the lights on enough to be able to get to the bathroom to go to the toilet or whatever, and you don't want the lights to come on full brightness just because you're walking around the house at night. But at other times of the day, it might trigger the lights to come on full illumination. And in neither case, if you had to go up, press a button or flick a switch and turn the lights on, the house has adapted to your needs, and that is what real home automation is about. So, hooking these up is actually pretty simple. They have connections on them for power, they just run off 12 volts, and they have a normally closed output, typically, for the alarm circuit. So what happens is, if it detects movement, the circuit is broken, and then your system is notified. If you don't care about security as such, you can just treat this as a switch. The output of it is just a switch that you can connect to your Arduino or your alarm panel or whatever microcontroller system you want to use. However, to make this really secure, there are some things you should know. So imagine that in your house you have some kind of a control system. Could be an alarm panel, could be a microcontroller. We'll just call it the panel for now. Like in security terms, the panel is whatever is connected to and controlling everything else. And over here you have your passive infrared motion detector with its detector panel there. And this can detect any motion in front of it. So you need to connect it back to the alarm panel or to the microcontroller. Now there are a couple of outputs on it. The most important is the alarm output. Now the alarm output is normally closed. So what that means is that it's a short circuit when it doesn't detect movement. If it detects movement, the alarm opens the circuit, and that way you can detect that something has happened. So the very simple way to connect this is to run a pair of wires all the way back to the panel from here, and you can just treat this as a normally closed switch. Now that'll certainly work, but you have some problems. What happens, for example, if someone crawls into the roof of your house and then short circuits across those wires? After that, the alarm can go off, or the motion detector can detect motion, but because the wire has been short-circuited, the signal will never go back to the panel, and they can walk around in your house all day and the system will never know about it. So we need some way to be able to protect against that. So what we can do is use a system called End of Line Resistors. Now there are a number of different schemes for this. A lot of systems use a single end-of-line resistor, and there is also a double end-of-line resistor scheme. I'll show you what I mean. Now, imagine that we have this panel and we take a resistor and we put it in series with the output. So what this means now is that there is a resistance through here. When the switch is closed, so the alarm hasn't been triggered, if we measure the resistance of the entire circuit, we know that it hasn't been cut, because if it's cut, it will go to infinite resistance. It hasn't been short-circuited, because it'll go to zero resistance, and it'll be at a known state. So if the alarm goes off, it breaks the connection, and it's effectively cutting the wire so it goes to high resistance. So then we have a system where we can detect whether the wire has been cut or short-circuited, and we can also detect an alarm event. Now we can't distinguish between an alarm event and the wire being cut. We just know that there is an alarm event of some kind. So you can get around that by putting another resistor in parallel with the normally closed output. So we'll call that one resistor A, and then we have the series resistor as resistor B. So what this means is that in a normal condition, the resistance will be the wire, and then through the normally closed switch, which bypasses resistor A, goes through resistor B, and then back down again. So now what we have is a situation where we can detect 4 possible states. Normally, it's just resistor B. Wire is cut, it's infinite. Wire is short-circuited at 0 ohms. If the alarm is triggered, then it will be the resistance of A plus B because they're in series. So now we're in a pretty good shape. We can detect wire tampering and we can detect alarm events. But there's something else we can do too to extend this idea even further. Now, typical motion sensors have a tamper switch inside them. And this is so that the alarm system can detect if the panel is opened or if any of the sensors are opened or physically tampered with, even when the alarm is not armed. Now that can be really important. Imagine a situation where you have a retail establishment, it might be a shop with lots of people going through, and you have motion detectors. Now normally during the day, the alarm system will be disarmed. So someone could walk up to a motion detector and tamper with it, and they could be doing whatever they like to it, and because the system is disarmed, they won't be detected. Now this is where tamper detection comes in. With tamper detection there is another pair of outputs, and once again this is a normally closed output. So that's another pair of terminals inside the motion detector that we can connect to. So what we do is instead of wiring this back to here, we take this resistor and run it into one side of the tamper switch. We come back here and then we add another resistor in parallel with the tamper switch. So we now have resistors A, B and C, which are in series apart from 2 of them being shorted out by the switches. Now you might say, what benefit does this give? It seems pretty confusing. But what it allows the alarm panel to do is detect whether the tamper has been triggered even when the alarm is turned off. And that means that the alarm system needs to be in one of 3 possible states. It can be in its regular disarmed state, in which case people can move around the shop or the house or whatever. The alarm won't go off, no alarms will be raised. But if someone opens a motion detector or tampers with any of the system, the tamper switch will cause the alarm to go off, because the alarm system knows that that is a tamper event as distinct from a motion event. Then it needs to be in an armed state, which is where either a tamper or an alarm event is going to cause the alarm to be triggered, or it can be in a maintenance mode, and that is what an alarm technician will put it into using a special code at the control panel before they start doing any maintenance that may require them to open up the panel or open up any of the sensors or make any other changes to the wiring. So what that means is that the alarm system can be checking the integrity of the entire system even while it's disarmed, and there might be people walking around inside the premises. So that's our objective. What we're going to do is wire up a motion detector using this triple end-of-line resistor system, so that from a panel, which could be an Arduino, we can detect wire cut, wire shorted, we can detect an alarm state, we can detect a tamper state. And of course we need to allow for tamper and alarm at the same time. And all of those events give different resistances depending on what resistor values we pick for here. So because alarm sensors are typically at the end of a fairly long wire, we want these to be moderately low values, like you wouldn't use 20 or 30k pull-up type resistors. So usually what's used is something like about a 4.7k or a 2.2k resistor. Now, the important thing is to make sure that the values for A and C are not the same, and that is what allows the panel to detect the different events. So the values that I typically use are for resistor A, I normally use 4.7k. For resistor B, I typically use 2.2k, and for C, I use 2.2k. So what that means is that in a normal operational state, the only resistance that matters is B. So the whole system will be at a resistance of 2.2k. If tamper has been triggered, this switch is opened and it will be B plus C in series, so 4.4k. If it's an alarm state, then it will be A and B in series, which means that it will be 6.9k. And of course, if it's tampered with and the alarm is triggered, it will be A plus B plus C, which means we would have a total resistance of 9.1k through the system. And of course we can still detect line cut and line short events. When choosing a motion detector, there are several factors to consider. Firstly, the type of lens. This is a standard lens motion detector, which means that it has about a 110 degree field of view, it has a range of between 7 and 10 meters or so, and any motion in front of it will be detected. You can also get a type that has a thing called a pet alley lens, and what that means is that it will attempt to ignore movement of small objects or objects that are very low. And if you have a cat that walks around inside your house and you want to be able to turn your alarm on, that might be the solution. So if you have pets, make sure you look for a motion detector that has a pet safety feature. The other thing is that you can have standard passive infrared motion detector or what's called a dual technology detector. Now, a passive infrared detector, if we crack it open, we can see what's inside it. They typically just clip open. Have this little detector sensor down here, and what that does is detect changes in reflected infrared radiation in front of it. Now, with a dual technology sensor, which I think I have to crack open from this end in this particular case, you'll see that it has the same sort of sensor down the bottom, but up the top, this is a microwave motion detector, which basically operates like a radar. So the one on the left is a standard motion detector, is infrared only. This one, which is the dual technology sensor, is infrared and radar. What that allows it to do is have greater range, better noise suppression, better sensitivity. So in general, the dual technology sensors operate better than the standard infrared sensors. But standard infrared is fine. Typically the dual technology ones are used in large rooms like auditoriums or unusual circumstances. So we'll just put that one aside for now and have a closer look at this one. Now there are a couple of things to notice. Firstly, if you look at this little spring here, it's connected to a switch. That's the tamper switch. So when the case is closed, the switch is pushed in and it's in its normally closed position. If this is mounted on the wall and someone opens it up, the switch is released and the tamper terminals go open circuit, which is how we detect tampering with the sensor. You'll also see that there is an LED up the top here, and this illuminates whenever the sensor is detecting movement. That is normally used by installers to do what they call a walkthrough test, and that is when all of the sensors are powered up, they're functional, and the alarm installer just walks through the premises, and you can see just by looking at the sensor whether it has detected any movement. Now that's great for testing, but a lot of people don't like that to be in use in normal operation, because what that allows is an intruder or someone coming through the premises when the alarm is disabled to probe the sensitivity of these. You can walk very slowly in front of it, for example, and see if you can move without triggering the sensor. But if you don't have that visual feedback, you can't tell how sensitive the sensor is. So here we have a little jumper. If we take this jumper off, that disables the LED. So typically what happens is that an alarm installer will do their walkthrough test, and then they'll go around and remove all the jumpers from the sensors so that there is no more visual feedback. There are a couple of other jumpers in here. One is the relay jumper in here, so we can set to normally open or normally closed mode. Now usually we want normally closed. And there is also a pulse count jumper. And what this allows is for you to change the sensitivity essentially of the motion detector. In its most sensitive mode, in single pulse, any movement in front of it will cause the alarm to be triggered. This can lead to some false alarms though. So by putting it into a different pulse count mode, it might be a 2 pulse or 3 or 5 pulse, it means that there need to be that many alarm events or motion events in front of it within a rolling window, usually 4 seconds, for the alarm to be triggered. That can reduce false alarms, but of course it also reduces sensitivity. And finally, across the top, we can see all of the screw terminals. There is a pair of terminals for positive and negative 12 volts, which is the power supply. There is the tamper output over here, which is simply wired with the switch. And there are the alarm outputs, which are normally closed circuit because of the setting on the jumper, and they go out open circuit when the alarm is triggered. Now you'll also see that there are some dimples in the back of the case here. Those are for various purposes. Those are deliberately weakened points in the case, and they can be used for screwing to the wall. You can use an electric screwdriver and then just drive a self-tapping screw straight through the case to attach it in position. And you can also use those and punch them out to run cable through. Typically the cable will come through in near the top of the detector, and will come through and then be screwed into the terminals here, so that the cable is totally concealed behind the unit when it's attached to the wall. The quick and dirty way to fit the end of line resistors, and this is what most alarm installers do, is just to bend them around, stick them into the screw terminals, put the wire in, screw it all together. Then you can just push these down out of the way. Now that certainly works, but I find that that's really annoying because typically when you're installing this, you'll be hanging off a ladder somewhere. It's kind of awkward. You're holding a screwdriver and all these bits in your hands. You don't want to drop things. So what I usually do is prepare all my motion detectors in advance by opening them up, taking the circuit boards out. It's really easy to do. It's usually only held in by one screw, and then just soldering the resistors directly across the terminals on the back in the pattern that I showed earlier, using one 4K7 resistor and a couple of 2K2 resistors. So that way, once you're up the ladder, your motion detector is all prepared, and all you've got to do is push the wires in, screw them on. It's a lot less that can go wrong when you're in an awkward physical situation. So here's another motion detector that I did this to in preparation. And I'll crack this one open, and you can't really even see them. Well, it's a bit difficult to see, but just under there are some resistors. They're hiding under the circuit board. And I've already connected up this wire. So I've drilled a hole through the case, and I've put some 4-core cable through it. I've got black and red for negative and positive 12 volts. I'm using the blue and white pair, and I'm connecting it from one of the tamper terminals to the opposite side alarm output terminal. And normally this would not be sufficient, but of course we have those resistors under the circuit board bridging across those terminals. So this is all set up ready to go with the triple end of line resistor system. So let's power it up and measure the resistance and see if this really behaves the way we expect it to. The PIR is now powered up. We've got 12 volts supplied down the cable from a bench power supply. And also I have the multimeter connected across the output terminals measuring resistance. As you can see, it's currently showing 2.2K, which is what we expect when the motion detector hasn't been triggered. If I move my hand in front of it, you'll see the resistance will jump up. It goes up to about 6.9K, which is what we expect given the resistors that are inside there. Now I'll shadow it with my hand, and you can probably just barely see the LED. If I hold my hand very still, it's now dropped out of alarm mode, and by moving again you'll see the LED turn on and the resistance has changed. And of course, if I shorted these wires or broke this connection, we would also get infinite resistance, or we would get zero resistance. So we've got all those cases covered. And now if I open up the case, which will trigger the tamper sensor, we'll see that the resistance is now about 9.1k, or a little bit under, based on the tolerance of these resistors. Now once it drops out of alarm mode, it's gone back to 4.4k, which once again is what we expect given that the system has line integrity, but the tamper switch has been depressed. And if I push the tamper switch, we can also see the value change. So now you have a motion detector with the end of line resistors in place. You have an Arduino. How do you connect them up? Well, let's have a look at a good way to do that. What you can do is basically imagine that your motion detector with its resistors inside is just a big variable resistor. So if you have a typical Arduino board, it'll have some analog inputs. So say we're talking about analog input 0. It's also going to have a ground connection internally with a terminal for it, and it will have a connection which is probably 5 volts or 3.3 volts depending on how it runs. Now if you connect a resistor between the high voltage and the analog input, and then you have another resistor between this point and ground, what the analog input will see is a voltage which is divided between 5 volts and 0 volts depending on these two resistors. So I'll draw this other resistor in here now just to show you what it would look like. And this is a classic voltage divider. Now what we actually have over here is our motion detector with its two terminals, and inside it's got all its resistors and various things that have been wired up. Basically this is a big variable resistor. So what we can do is simply take the two terminals that we want to wire one through to ground on the Arduino. This resistor disappears because it's been replaced by our motion detector, and then we wire this through to the Arduino. So what we have now is an analog input that can read different values depending on the state of the motion detector, because this resistor is fixed. So if we put, say, a 4.7 kilo ohm resistor here, and this resistance will vary between 2.2k or 4.4k or 9.1k or whatever, depending on the state of the alarm of the motion detector, we can then detect those events at the Arduino. So then just imagine that this is a long bit of wire. It goes from here all the way through to your sensor. Now this is going to expose an analog pin to a very long piece of wire, which is effectively an antenna. Now that's not really ideal. There are a couple of things that can be done to protect it. What you can do is put a resistor in series at this point. This could be, say, a 1k resistor. That allows the analog input still to detect the voltage at this point in the voltage divider, but it gives a bit of inrush current protection. It should reduce likelihood of damage to the analog input. You can also do things like put lightning suppressors or a protection Zener across this. So we could have a Zener here, or a lightning protection system, and that would prevent the voltage on this input from going too high and hopefully protect this. These sorts of protection systems are often found on USB connections, so these parts are pretty easily available. So as you can see, it's basically an Arduino and a couple of resistors, and you're done. In fact, you could get away with just an Arduino and one resistor if you really wanted to. So you could just wire that up yourself. You could take your Arduino, take the analog inputs, and put a resistor in place, but that gets really annoying. And also you need somewhere handy to wire up the power, because we also want 12 volts going to our motion detector. So what I did was laid out a little shield. This is a security sensor shield that I designed a while ago, and it's got handy screw terminals on here for the connections to the infrared motion sensors. It's got connections to V-in, or to the screw terminals here, which means that you can supply 12 volts to your Arduino. In fact, what we can do is, I'll just stick this on the Arduino right here. If we ran 12 volts into here, then we would have 12 volts available on each of these screw terminals. And we also have the two connections for the sensor line. Now this shield already has 4K7 resistors in place on it, and it also has an LED next to each screw terminal so that the Arduino can display the status that it's detecting. All the connections are now in place. When I was designing the shield, I also added some holes so that I could run cable ties through and mechanically mount the cable really strongly. That's very important because you need to make sure that these connections aren't going to move. You don't want pressure hanging on the screw terminals themselves. So now we can just chuck this onto the Arduino, and then if we apply 12 volts to it through the Arduino's power, you can see we've got power on the shield, 12 volts. The motion detector is now powered up. It's in its warm-up mode. Which reminds me, when you first power these up, they will always act as if they're triggered for a little while. That's because it needs to stabilize its internal sensor. So when you first turn it on and power it up, if it looks like it's just always triggered, don't worry, it's not broken. Let it sit there for a minute and it should settle down. Just for some quick feedback, I've loaded up a sketch on the Arduino, fitted an LCD shield, and it's just reading the analog input and giving us the value displayed on the screen. And it's also looking at whether the number is within a certain range, and it's showing the state of the sensor. So at the moment, the sensor isn't triggered, it's showing normal value. Its analog reading is 323 out of 1023. If I move my hand over the sensor, it goes to 606, and the Arduino then knows it's an alarm state. Now I'm hiding in the doorway to my home office because just up around the corner there is a motion detector. It's now connected up to an Arduino, publishing to MQTT. So if I step into the garage, it should pick up the motion, and the lights come on. Brilliant. So check out the website for all the code. There should be detailed instructions for how to make this happen. See you next time.